Okay, let's talk about today's topic, which is probability. And what is probability really all about? So probability, often you see we use the letter P, probability, for obvious reasons. And really what we do with probability is we try to quantify uncertainty. Now, there's a bit of vocab that's involved, but quantifying uncertainty really means that we just give it a number. So when I say we're trying to quantify something, give it a number, give it a number. And then the question becomes, okay, well, what are we trying to give a number to? And the thing that we're trying to give a number to is some uncertain event. So let's put that there, uncertain event. We're trying to put a number to an uncertain event, and often an event can be described with a letter like A. And so the probability of A happening is written like that. And when we talk about calculating, what we talk about is the number of possible outcomes for an event, so number of possible outcomes. And we also talk about the number of favorable outcomes. So an example would be if I had a dice, which is a very popular way to describe probability, we would say that there are 6 possible outcomes if you throw a dice. Let me put this here. 6 possible outcomes. And if I have an uncertain event A, let's say throwing an even number. So what is the probability of throwing an even number? Maybe I should even use the letter E if I'm going to say even number. That makes sense. So if you're throwing a dice, the probability of throwing an even number, well, the number of favorable outcomes would be 3, because 2, 4, and 6. And so we would say probability of getting an event E would be 3 out of 6, or we could say it's 50%, or we could say it's 0.5. So this is the most basic formula we use in probability all the time. And when we calculate the probability of an event, it's always going to be between 2 extremes. The one is 0 and the other one is 1. This side is going to be certain, so 100%, or 1 is certain. And on this side, we have impossible, which is a 0% chance of happening. Now, there's a bit more vocabulary that needs to come still, but that's the basic idea. Give me a thumbs up if that looks vaguely familiar to you. Give me a thumbs down if that feels a bit like, you know, what are the man talking about? Okay. Fantastic. Well, then let us not delay your journey any further. That was just my little summary of what we're doing. So if we use more technical words, what does probability mean? Well, here's the definition. We calculate the probability of an event occurring. We are calculating the likelihood or the possibility of that event taking place. So probability is just the measure or number of the likelihood of an event occurring. Now, it still sounds very like wordy, but if we look at the scale below, impossible is 0, certain is 1. If we are halfway on the probability scale, we say it's 50-50 or an even chance. And the way we could represent that would be 50 out of 100, or you could say 50%. If it's more to the right, maybe it's like 80% chance, we would say it's likely. If it's more to the left, maybe like 1 in 6, which is about 16.6% chance, that's unlikely. These are words we use to describe probability in ranges. Okay, so those are all the basics. Here is the most important formula in the whole of probability. The probability of an event A is described by this formula. Can you tell me using that formula, what do you think the answer to this question is? Now be careful, because sometimes the question has a couple of parts. So I don't doubt that 6 is the total number of outcomes, but the favorable outcomes, read carefully. What is the probability that the score is a factor of 6? Now, if you want to visualize, sometimes we use something called set notation. We use S for the whole sample space, or all the options. So there's all the possibilities. Now, for your event A, a factor of 6. Well, a factor of 6 is a number that divides into 6 exactly. So it would be 1, 2, 3, and 6. So what we have here is, if you get a 1, 2, 3, or 6, then the event A has happened. So what is the probability of A occurring? Well, there's 6 items that are possible. 4 of them are favorable. I like to draw like a little smiley face. 6 of them are possible. What is the probability of A occurring? Well, it's going to be 4 out of 6, which is the same as 2 out of 3. And if we were using the words from above, we would say that it's kind of likely that you actually will get a number that's a factor of 6. So what we've noticed is the devil's in the detail. Really understanding what it means to be in the set A or the event A is really where this question, is figured out. Okay, let me know in the chat if you're feeling very confused. I'm assuming that most of you understood that, and so I'm going to go on to the next question. It's a similar type of question, and I'm going to let you read through this and then try and give me an answer. What do we think? What do we think? What are the number of possible options, and what does it mean to be a favorable outcome? Now, all I'm doing here is I'm listing what are the outcomes in each event. And S just stands for all the possible outcomes, or the sample space for the event. So what is the probability that I get an odd number? Well, there's 5 here, 5 options, and here there are 3. So I get 3 out of 5. And if I wanted to write that as a percentage, it would just be, there's a 60% chance of getting an odd number. Letty, where did I lose you? Let me know. How is it 3? Because Letty, if you look at the collection, there aren't 6 options anymore. There are 5 items that are possible. You can count on the picture, or I drew a little set which said S, and S has 5. S is just a letter I'm using for the sample space, and there are 5 options. So that comes from here. In the 5 options, the odd numbers are 1, 3, and 5. And so there are 3 options that are odd. And so that's why if I'm asking what is the probability that the number it lands on is odd, there's a 3 in 5 chance. Yes, that's exactly what we're doing. No problem. Let's do another one like this. If this time, this is one of those fancy dice like you get on these fancy board games, and the dice has numbers 1 to 8. if the dice is thrown once, what is the probability that the face lands uppermost with a prime number? So I want you to think about the definitional formula for probability, which is how many possible outcomes, so number of possible, and then for this particular event question, how many favorable outcomes are there? And that will tell us what the probability of this thing happening is. Okay, how are we doing? So I think it's still 8. Well, I know it's still 8 in terms of possibles, but which ones are primes? Well, 2 is a prime, 3 is a prime, 5 is a prime, 7 is a prime. So how many options are favorable for this event question? It's 4 out of 8. There's no 4 out of 8, but 4 out of 8 is the same as a half. And so the correct option is C. Okay, so we're just getting a feel for the main formula in probability. So let's just keep going with these ideas. Give me a thumbs up if you're feeling good. Give me a thumbs down if you're feeling like a bit like, whoa, 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 whoa. Okay. So sometimes what we like to do is they ask you questions about the probability scale. And so I don't know how much you know about SpaceX and all these things, but if you had to estimate the probability for the event, man one day will set foot on Mars. Now, this is a different type of question because it's hard to have possible outcomes or favorable outcomes, but knowing what you know about the world, of the options available here, which of the arrows shows the best position on the probability line for the event man will one day set foot on Mars? And this is more just about understanding the scale. Which one do you think it is? I think you could make an argument for 2 of them. Given that we made it to the moon, so we know how to get to the moon, and given that we now have rockets that are pretty powerful, I want to suggest, and this is a bit of an open-ended question, but either D, so it's very likely, or C would be good options. You can sort of debate this question, but in reality, I think that it's very likely that we'll one day get to Mars. And so that's why you would be down in this end of the probability scale. But that's more just a judgment question. And a little bit, it relies on your general knowledge. So it's not likely to come up in an exam, but I just thought, interesting question. Okay, let's keep rolling. Let's do another one. This is a word probability problem. So you're given the letters of the word Mississippi, and you write each letter on a separate page. You put them in like a hat, and you take out one without looking. What's the probability that you get an I? What is the probability that you get an I? So I'm starting to shorten this even more to possible and favorable. So possible is 11 if I've judged. Yep, 11 letters. What is favorable for the question over here? Well, I see an 1, 2, 3, 4. So we must get 4 out of 11. And that would be A. Okay, so they become almost quite predictable when you understand that formula of possible outcomes over favorable. Let me take it up a notch. Now we are going to the land of cards, and I'm sure you've all played cards before. And when you pull a card out of a deck, you don't know what comes next. But what they are telling us is there are 52 playing cards in the deck, and there are 4 queens and 4 kings in the deck. What is the probability the card chosen is a queen or a king? So maybe I would use to say like probability of the king. What's the probability of getting a king or a queen if you're getting a card from the pack? Now this kind of has to be 52 because they told us there's that. Now, if there's 4 queens and 4 kings, those are all favorable outcomes. So that must be 8 out of 52, but there's no 8 out of 52 that I see here. But I know what's happening. It's an equivalent fraction. And everyone is saying B, and I see what you've done. You've divided 52 by 4 to get 13, and you divide 8 by 4 to get 2. Well,
Goodbye, should be wearing a ski mask because you're rotting me blind.
Oh, mute all there. Okay, so we should be getting 2 out of 13. So that for me is B is the correct option. Okay. I'm looking at the chat, it looks like we're mostly on board, so that's fine. Let me know if I've lost you. Let's do another type of question here. Now, before I start, I would love somebody to try and explain. You can put your hand up or you can put it in the chat. Why is this question different to the previous one? Because now this question is about tossing a coin 3 times. What makes this different or more difficult or whatever it is compared to the ones we've done so far today? We are not given the sample space. Flamelo, you're on the money. Kat, 3 events? Yes. So we call this a compound event because there's lots of like little events inside the main event. And it repeats itself 3 times. So what makes this difficult is it's hard to know, like that formula that we used before was just favorable outcomes over possible. And we need a way of keeping track of what are the favorable and what are the possible. Does anybody have any ideas from your studies about how we could visualize this? Because that's really what we need, a tool to help us. Any ideas from class? Are they mutually exclusive? Lorato, that's an interesting question. It's not relevant for this type of question, but we'll come back to it. Aha, yes, a tree diagram. So one of the tools, so it's, I think Sate has said a tree diagram. So let me see, if I have 1 coin, give me a thumbs up if you feel that for 1 coin, that would be a good tree. So, or 1 toss, let's say for 1 toss. You happy? Okay, now, if I did this, are you happy? Give me a thumbs up if you agree. Give me a thumbs down if you disagree. To represent 2 tosses of a coin, this shows me all possible outcomes. Heads, head, heads, tails, tails, heads. Okay. So it's been going well so far. So let me see if I can extend this idea. I think a third toss would just show me, I would just let the branches keep growing. So we'll make this the third toss. So if I visualize heads, 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 that's one option. Heads, heads, tails is another option. Heads, tails, heads is an option. Heads, tails, tails is an option. What I love about the tree is it takes the hard work of keeping track of what's going on out of the picture for me. It just shows me if I get a tails first and then I get heads and heads, that's an option. So I want to know how many possible options are there if you throw a coin 3 times, or if you toss it 3 times. Super clear, I absolutely can explain. So if I toss a coin once, there are 2 outcomes. I could get a heads, or I could get a tails. So that's if I toss it once. If I toss it twice, I could get heads, heads, or I could get heads, tails, or I could get tails, heads, or I could get tails, tails. So that gives me 4 options that are possible. Now I need to know if I have 3 tosses, how many options? And I think following the pattern, we should get 8 options. 1, 2, 3, 4, 8 possible options. So there are 8 possible options if you toss a coin 3 times. But that's not the question. The question says, what is the probability of obtaining 1 head and 2 tails? Now, if I look at my tree, I want you to go hunting for pathways which have 1 head and 2 tails. How many paths are there that have 1 head and 2 tails? It can't be that. It can't be that. It can't be that. But the first one I notice, heads, tails, tails. So that is one favorable outcome that's possible. How many more are there in this tree that you can notice that have 2 tails and 1 head? So tails, heads, heads won't work, but tails, heads, tails could work. And then we could also go tails, tails, heads. So I've got 8 branches on the tree, but 3 of the branches are favorable for this question. So we would have, there's a 3 in 8 chance that if you toss a coin, that you will get 2 tails and 1 heads, which is the option C over here. Okay, now that is in lessons 4 and 5. I'm going to go over the tree diagram in a lot more detail. Today is just a getting going. Oh, Tebogo's got a lovely question. Why is it out of 8? So if you look at my tree, each branch is one possible outcome. So the outcome heads, heads, heads. How many possible ones are there? Well, that's the first one. That's the second option. Then I've got 3, I've got 4. So up to this point, I've got 4 options. Then there's option 5, option 6, option 7, option 8. So it's because there are 8 branches on the tree. I hope that so Relobogile, you can just use the no import. It's not. It actually, there's 8 options. You can visually see it. Let's do one more, then we'll have a break. You'll see it. If we do another example, you'll see how this works. So just hang in there. Let's do this question. Okay. If I give you this situation, I want you to draw a tree. Okay, draw a tree that represents the possible options if you throw a dice. So a six-sided dice, you throw a dice, how many options? And then at the same time, you throw a fair coin. How many possible options are there? I want you to draw a tree for me and tell me how many possible outcomes are there for this event. Take a moment to draw your tree. It's not a very nice looking tree, but I think my first level of my tree would look like this. Because those are all the possibilities for a six-sided dice. But, okay, Linda, I'm not going to talk about independent events. They are independent of each other because the coin doesn't affect the dice. They're separate. But at this stage, all I'm doing is trying to visualize how many possible options are there. And I want to suggest, what are the two options that if I get a 1, what else can happen that is uncertain after that? What are the two options on this branch of the tree? So let's just stay with me and focus for now. I'll get to all the questions in a moment, but what are the two options here? If it's a coin, wouldn't it be heads and tails? So two options are throwing a 1 and then getting a heads, or throwing a 1 and then getting a tails. Yes, and Paul, I agree. Now, the rest of my tree is each number has the possibility of having a heads or a tails that goes with it. Now, I know I'm not drawing the prettiest tree in the world, but it's the idea. How many possible outcomes are there for this event that is a little bit complicated because it's throwing a dice and a coin at the same time? How many possible outcomes are there? Yes, this is called a compound event, which has two little parts. Sate, you are on the money. It is 12 possible outcomes because it's 2 outcomes are possible for each number. So you could count them 1, 2, and so on up to 12. Okay, now, what is the probability of getting a multiple of 3 on the dice and a head on the coin? So I'm going to go hunting for my favorable outcomes. So where am I going to go hunting? I'm going to go hunting on the 3 and the 6 because those are multiples of 3. But just being a multiple 3 is not enough. Then and you also have to get a head on the coin. And means you need both. So 3 and that one would be a favorable, or 6 and that one. So what is my favorable number of outcomes going to be for this question? What would be a good result? There's 2 options that are happy days for me. It's 3 and heads or 6 and heads. So there's a 2 in 12 chance, but there's no 12, or there's no 2 in 12. So which option of the 4 is going to work? Okay, 2 in 12 is the same as 1 in 6. And so we would get A is the correct answer. So there's a 1 in 6 chance that when you throw a dice and a coin at the same time, that you will get a multiple of 3 and heads. So it's not very likely, actually. It's quite a small chance. All right, I've been bringing so Sipo Sikle, all that you need to look at is this formula. So if you look at, the question is, what is the probability of getting, if you throw these 2 things, of getting a multiple of 3 and the heads on a coin? And there are 12 possible options that you can see on the tree, but only 2 of them are favorable because there are multiples of 3 and the heads on a coin. And so there's 2 in 12 or 1 in 6 chance of this happening. I will go over this a little bit more after the break, but I think it's important that we stop now and have a break. So let's turn on our cameras and then let's stand up. Kia, if you could please encourage our students to join us and to give a shout out to those who are participating. Let's start by just standing up and swinging our arms and then twisting a little bit. And as we start, you feel that I go a little bit further. Okay. Then I want you to stretch out your hamstrings. Let's do something different. So stretch out your hamstrings. Oh, that feels good. Do that. And then let's stretch like this. Like this. Okay, swing out the arms again, nice and loose, like a piece of licorice. And then let's do some air skipping. So we're going to do 20 in 3, 2, 1, go. Yeah, 10 more. And have a seat. I hope that your body feels like it's had a bit of oxygen and a bit of blood flow. And the challenge question for today, or the brain puzzle, is how many squares are there in this picture? How many squares do you think there are in this picture? Get those answers coming in the chat there. I'll give you a hint. So we have the 1 is the big one. There's clearly going to be 9. But there are a few more sneaky ones hiding in there. I'll give you one hint. I can see a square there, and I can see a square there. And I can see a square there, and I can see a square there. I know, Nompuleyo. There's a lot of things going on there. So for me, unless somebody can, and I encourage you to to think, I get 14. Unless there's something I've missed, I get 14. I know. There's a lot of squares in the house. Because the moment you start to break this, you get rectangles. You don't get squares anymore. Okay. So this is a great question. You can give this to somebody you know and see, you can confuse them. So I don't know if I can't get any more than that, but that's what I get. I get 14. Cool. All right. Let us get back to our introduction to probability that we were doing already. So we were doing these tree diagram type things. And let's see what other types of questions we might sometime get. Well, let's do this one. just to kind of get us going again. A special die is made in the shape of an icosahedron, and the faces are numbered with 1 to 20. When the die is thrown, there's an equal chance of each face landing. If the die is thrown once, what is the probability that the face that lands up has a number that is a factor of 20? So if you think about what this question is asking, it's clear that the number of possible outcomes is 20. The difficult bit is what is a favorable outcome, given that something has to be a factor of 20. What are the factors of 20? So 1, 2, 4, 5. What else? 6, no. 7, 8, no. 9, no. 10, okay. And then 20. 2, 3, 6. So it feels to me like the answer is going to be 6 out of 20. And in that case, which option is going to fit that? Well, it's not D, it's not B, it's not A, and then 3 out of 10 is the same as 6 out of 20. So it should be C, which, judging by what I'm seeing in the chat, look good. Okay, all good, all good. Now, when we talk about probability, there is such a thing as an event and its complement. And this is an example of complementary events. Complementary events basically are two events that together add up to the probability of 100%. So an example here is the probability that my train will be late tomorrow is 1 out of 10. What is the probability that I will not be late? Just using normal logic, like, either you are, if you think about it, you're either late or you're not late. Now, if you know the probability that you'll be late is 1 out of 10, what is the probability that you won't be late? Okay, and I think most of you know that it's 9 out of 10, because together the two outcomes must add up to 1. Now, a fancy way of doing this, using probability notation, we would call this L. And if it's not L, we just say L dash. So sometimes in maths, we like to use like abbreviations. And so if I say L dash, that's everything that's not late. And the way we would write this in probability theory is we say the probability of being late plus the probability of not being late will equal 1. Because these two sets, L and L dash, are complementary sets or complementary events. If you basically together, they fill all the possible outcomes together. Are we allowed to answer in percentage? You are. So an equivalent to this would be 9 out of 10 could be 0.9, or it could be 90%. Those are all valid. 1 is the sample space, yes. So there's always a probability of 1 or 100% that you will get one event out of all the possible events. Let me show you another question that is similar to this, just to get you into the vocab of it. So if I tell you the probability of an event A occurring is 3 out of 4, what is the probability of A dash, or the complementary event of A occurring? Now remember that with complementary events, we know that together they must be equal to 1 or 100%. so if I know that this is 3 out of 4, plus this is 1, well, I think the only way that would work is if that was 1 out of 4, which is what everyone is saying in the chat. And so D is the correct option. And so these are examples of complementary events, and complementary events also have this, sometimes we say if it's this and not that. Let's do another one like this. A fair die is thrown. What is the probability that the score is not a factor of 6? So not a factor of 6. What's the probability of that? So we actually did the probability of something being a factor of 6 earlier on in the lesson. And that was the probability of something being a factor of 6 was 1, 2, 3, so it was 4 out of 6. The probability of not being a factor of 6, well, still 6 options, and it's only going to be 4 and 5, which is 2 out of 6 options. So the probability of not being a factor of 6 is 2 out of 6, but there's no option for 2 out of 6, but it's the same as 1 out of 3. And we get that. Give me a thumbs up if you're following okay. Give me a thumbs down if you're feeling a bit lost by what I'm doing. Okay. We're just covering some probability basics today. You know, we're just kind of introducing ourselves to interesting ideas in probability. Why can't it be 2 over 3? Basically because the chances of getting a factor of 6 are 2 out of 3. The chances of not getting 2 out of 3 is going to be what's left basically up to 1. Okay, now here is another visual structure that we can use to help us see outcomes. Now imagine that you are throwing 2 dice. Okay, so you've got 2 dice, and what you're doing is you're adding their scores together. So an example would be if I throw 1 and 6 on my 2 dice, 7 would be my number. If I threw a 3 and a 2, then if you add them together, you get 5. Now, what I've got here is what's called a sample space diagram. It's trying to get you to visualize all the possible combinations that you could get for the sum of 2 dice. And it also looks a bit like a table. And so if we are imagining that if you threw a 1 on dice 1 and a 1 on dice 2, you would get a sum of 2. If you threw a 2 on dice 1 and a 1 on dice 2, you get 3. And over here, we would have 4. Using this diagram, what do you think is going to be in the position of the red star over here? What do you think is going to be in the position of the red star over there? What do you think you threw on dice 1? What do you think you threw on dice 2? Well, you must have thrown a 2 on dice 1, and you must have thrown a 5 on dice 2, which means behind the red star must be the sum of those 2 items, which is 7. And so all the table is doing is it's just making it easy for us to visualize all possible outcomes, which, as you can see from today, is pretty much visualizing the outcomes is half the battle with probability. Okay, let's do, see if we can do another. Okay, let's do this one. So, 2 fair dice are thrown. What is the probability that the 2 scores do not add up to 7? And I'm actually going to leave the question above on the screen to help us with this one. So let's see if I can get it. Maybe I should just break it down. So we have a question, and or maybe I'll draw a new table. We're throwing 2 dice, and they want to know what the probability that the 2 scores do not add to 7. I'm struggling to see all the possibilities. And so what I'm going to do is I'm going to draw a table that helps me. So I know for the first dice, I could have 1 to 6. For the second dice, I can also have 1 to 6. Let's start by asking how many possible outcomes are there? Well, actually, you know what? Let's fill out the diagram first so we can visualize what is possible. So for me, I'll fill out the first 2 columns. You guys fill out the rest and then see if you can identify what do you think is the correct answer here. So if we look at this, it feels to me like there are 36 possible outcomes. Because basically I've got 6 here, 6 here, 6, 6, 6. But now, what is a favorable outcome in my table? So if I look at that, a favorable outcome is not adding to 7. Well, how many of them add to 7? Well, this adds to 7, 1, 2, 3, 4, 5, 6. So those ones add to 7, but all of the other ones, they don't seem to add to 7. So how many do you think, how many options do not add up to 7? Yeah. Well, what's left over? You had 36, you got rid of 6 of them, so it's 30 out of 36. Now, there's nothing out of 36 here, but I think there's a 5 in 6 chance that you get a sum that does not add up to 7. Using, okay, how is it 36? Saskia, if you look at the options, there are 36 different combinations that are possible if you add 2 dice together. You can get 1 and 1 and get 2. You can get, so basically I was just adding up 6 for that row, 6 here, 6 here, 6 here, 6 here, 6 here. And so there's 36 possibles. But for this question, I want all those options that do not add up to 7. So in this row, there would be 5 options that don't add up to 7. In this row, there would also be 5 options that don't add up to 7. In this one, there would be 5 rows, 5 options that don't add up to 7. And you kind of see the pattern there. And together that must give me the 30. Yes, Kimmy, what is your question?
So how did you get the 5 out of 6?
How did I get the 5 out of 6? The short answer is you could use your calculator. So if you go 30 divided by 36, try out your calculator, or I divide the bottom by 6. So 36 divided by 6 is 6. What is 30 divided by 6? It's going to be 5. So I just basically divided top and bottom by 6.
I think I'm going to stick to the calculator.
No problems. You bought one, you may as well use it. Okay. So then just a follow-up question. What is the probability of getting a sum equal to 7? So you worked out the probability of getting a sum that does not equal 7. I want to know what's the probability of getting a sum that is equal to 7. So there's still 36 possible options, but only this time, there are only 6 favorable ones. The ones on the diagonal, which is the same as 1 out of 6. Ayabonga has asked, is it okay if I write 6 over 36 minus 1? You get the same answer. Yes, that's completely fine, Ayabonga. You using the complementary identity, which is completely fine. All right, everyone, we are going to stop there for this evening. We will carry on in the next lesson with some more probability basics. Thank you so much for attending today. I hope that you enjoyed the lesson. Please give us your honest feedback so that we can adjust the pace accordingly. And I will see you all on Wednesday. Pleasure, Sonic. I'm glad you enjoyed it. Today was just about getting to meet a new friend, basically. You know, like we kind of just reintroducing ourselves to probability. Tomorrow we start Venn diagrams in the next lesson. We'll do a bit of Venn diagrams because a Venn diagram is just another way of visualizing outcomes. I mean, that's basically all probability is a question. We're uncertain about something. How do we visualize it? Then we count it.